Today I want to look at hypothesis testing. I can explain this best if I look at examples. Let's first of all look at this one. Over a period of many years, drug A has been used to treat a certain disease with a cure rate of 35%. A new drug B is tested on a sample of 40 people who have the disease, and 19 are cured. Is there any evidence that drug B is better than drug A? Well, we start this by assuming that there is no difference between drug B and drug A. So that's the first assumption. If this is the case, then the cure rate for drug B would be 35%. And the number of people cured using drug B in a sample of 40 would be binomial B 0.35. I've summarized that here, and you can see there no difference between the two drugs, cure rate for B also 35%, and the number cured in 40 would be binomial 0.35, n equals 40. I've drawn here the probability histogram for that. And we're trying to decide, when we do our sample, whether drug B is better than drug A. What numbers would cause us to think that drug B was better than drug A? If we had an answer of 24 cured with drug B, although that could have happened with drug A, here's the probability. It's very unlikely, so this would be a surprising result. And if we got a result around about 24, 25, it would be surprising, and we would think that probably drug B is better than drug A. If, on the other hand, we got 16 cured, we could easily have got 16 cured with drug A. It's not very surprising. Look at that huge area there. This is what we're looking at each time. We're looking at that area. If this area is small, then this answer is surprising. 23. Not very likely to get 23 with drug A. So if we get 23 with drug B, we're probably better off. So we're really looking for the area on the right-hand side of the blue line. And we should be careful to place the blue line on the boundary between the bars. Putting it there where we're partly including the bar for 19 isn't really much help. So we're trying to find somewhere where that area to the right is small enough for us to be surprised. We often choose 5%, sometimes different numbers. And so we're looking to see really whether the area to the right of the blue bar in any of these positions is less than 5%. Well, let's start with the area greater than or equal to 19. If I take the area greater than or equal to 19, I'm looking at the probability that x is greater than or equal to 19. Using my probability tables, 1 minus p x less than or equal to 18, and that is equal to 1 minus 0.9301, and that is 0.0699. Now that's bigger than 5%. So what happens if we take our line out a little bit? If I take my line out, didn't want to do that. If I take my line out to greater than or equal to 20. Probability that x is greater than or equal to 20 is 1 minus the probability that x is less than or equal to 19, which is 1 minus 0.9637, which is 0.0 0.363, and that is less than 5%. If I go out one further and look at the probability that x is greater than or equal to 21, I get 1 minus probability x less than or equal to 20, which is 1 minus 0.9827, which is 0.0173. And of course, that is going to get smaller and smaller as I go out. So we've found here that if we put this line on the greater than or equal to 21, the area to the right is 1.73%. If we put it there, can't get it to move to the right place. If I put it there, then the probability is 3.63, still smaller than 5%, whereas if I move it up to there, my probability now is greater than 5%. And so we say that for 5%, we take 20 as what's called our critical value. I've summarized all that for you here. But we must place the blue line on the boundary between two rectangles. We look at the area to the right of the blue line, very often choose 5%, sometimes different. We can't get exactly 5%, so we have to look as we did here. And then we choose the number 20, because that, if we move down 22, 21, 20, 20 is the smallest number where we're still under 5%. When we get to 19, we go over 5%. And so the smallest value, n of x, where the probability that x is greater than or equal to n, we include n in this, is less than 5%. In this case, is n equals 20. Now, what does that mean? If n is greater than or equal to 20, our number cured, we would be surprised. We would reject the assumption that there is no difference between the drugs, and we were testing to see whether one was better than the other. We would conclude that drug B is better than drug A. In this case, 19 people are cured. 19 is less than 20, which is what we refer to as a critical value. So we reject the assumption that drug B is better than drug A. And our conclusion is that there is evidence that drug B is not better than drug A. Remember that statistics never give you definite answers. Okay, now let's take this on and formalize the way that we write this out. Your exam board is really quite fussy about the way in which you write out your significance tests. The first thing you have to do is write down H0. This is what's called the null hypothesis, the sort of no difference hypothesis. But you're not allowed to use words, just use the red. H0, P is equal to 0.35. What are we testing? We're testing to see whether drug B is better than drug A. In other words, whether the probability, the proportion goes up. So H1 is called the alternative hypothesis. A little bit misleading. This is your conclusion that you will make if you reject H0. So that is H1, P greater than 0.35. Then I like to see you write down the significance level. In this case, we're using 5%. And we're also using a one-tailed test. We are using the idea that P is greater than 0.35. We're testing whether B is better than A. We're not testing whether B is different to A. If B was different to A, then we would be surprised if P was too small or too big. In this case, testing B better than A, we're only going to be surprised if P is too big. So there's your one tail. Then we look for our critical values. This one was the one that we referred to, x equals 20. And the critical region is the area on the right-hand side and including x equals 20. So the critical region is x equals 20. So this you must do each time. Then we draw a conclusion. Right. 19 is what's called the test statistic. It's the observed figure. It is the statistic which we are testing. 19 is less than 20, which is our critical value. Therefore, 19 does not lie in the critical region. 19 does not lie in the part which would surprise us. Therefore, we reject H0, written in red, and we conclude, and here there is evidence that, we can't be certain, there is evidence that drug B is not better than drug A. In the next video, I will go on to do another example and show you more about significance testing.